Yep. Okay. So I'm very pleased to be able to say that Jelani Nelson is our speaker today. He's a professor in the Electrical Engineering and Computer Sciences Department at UC Berkeley for about the last year, we just found out. During his career, Jelani has won several major awards, including a Presidential Early Career Award for Scientists and Engineers, an Alfred P. Sloan Award, and the George Sproul's Award, among others. In addition, Jelani has also founded Audis Coder, I read online, a summer program for teaching computer science and algorithms to high school students in Ethiopia. And today we're lucky enough that he's been willing to join us and tell us some of what he knows about Johnson-Lindenstrauss embeddings. So with that, I'll turn things over to Jelani and let him tell us some of what he knows.
Okay, thanks for having me. Can you hear me? Can you hear me well? So?
Yep.
Okay, great. So I'm going to talk to you about terminal dimensionality reduction. I'll define that soon. Our starting point for today's talk will be the Johnson-Lindenstrauss lemma, which is a lemma about dimensionality reduction in Euclidean space. It says that if you have n points in Euclidean space, then you can map to dimension log n and preserve the distances multiplicatively. Specifically, for any given epsilon, you can map to dimension 1 over epsilon squared log n and preserve all Euclidean distances up to 1 plus epsilon via some embedding f into lower dimensional space. Okay, so also the proof of this theorem, all the known proofs of this theorem, f is actually a linear map. So x gets mapped to pi x for some matrix pi. So I'm a computer scientist, and computer scientists care about this Johnson-Lindenstrauss lemma because of applications to, let's say, high dimensional computational geometry, right? So let's say you want to have a data structure for nearest neighbor search, right? So you have a database of high dimensional vectors, like, featureized data, like one thing computer, raising hand, yes, question? Amir Sagiv. I see some raising of hands. Is there an issue? I don't know how to see. So
if people will be putting questions into the Q&A, he says it's by mistake, so it's fine. We can manage the questions for you and sort of do it.
Okay, great. So yeah, just interrupt me if there's some questions that I'm happy to address. Okay, so right. So the idea is, you have some data which is high dimensional. So people treat emails as, a bag of words, which is basically a vector indexed by all words in the dictionary. And then by looking at angles between different emails, you can tell whether, say, something is spam. So you have some classifier based on these high dimensional vectors, which represent emails, that a classifier you train. And it's using geometric information to make a labeling of likely spam versus likely not spam, right? So the idea is, whatever algorithm you're using on this high dimensional data probably has runtime that depends on the dimensionality of the data, and probably grows as the dimension grows. So if you have a way of, in pre-processing, transforming your data into a lower dimensional representation, then probably all those algorithms are now faster and use less memory, etc. Also fast linear algebra algorithms. So it's known that you can use such embeddings, or embeddings that are related, to do, let's say, faster approximate least squares regression or faster approximate PCA and other linear algebra tasks. I already mentioned, training in machine learning, speeding that up by reducing dimension, etc. Okay, so that's why computer scientists care about this thing. And that's the JL lemma, which has been known since the 80s, 1984. And what I'm going to talk about today is a new theorem from last year, joint work with Shyam Narayanan, who's now a graduate student at MIT. At the time, we were both at Harvard. He was an undergrad. And what the difference is between this theorem and the JL lemma is what I highlighted in blue, and also what I crossed out. So it's the same setup. You have n points now in d-dimensional Euclidean space. You're given an epsilon. You can map into dimension 1 over epsilon squared log n, such that in the original JL lemma, it says, for all pairs of points in the original point set, the distance is preserved, right? JL preserves distances within the point set. terminal dimensionality reduction preserves distances not only within the point set, but also from vectors in the point set to the rest of space. So for all x in the point set, for all y arbitrary, in all of Euclid, in all of space, in all of d-dimensional space, the distance from x to y is approximately preserved. Okay, now, such an f cannot be a linear map. Maybe an easy way to see that, well, I mean, if you want to have dimensionality reduction, it can't be a linear map. An easy way to see that is pretend that capital X is just a single vector, which is 0. Okay, so now you're telling me that a linear map preserves all distances from all vectors in space to 0, right? So that means that pi x minus pi 0 is very close in norm to x minus 0. So in other words, pi x has roughly the same norm as x for all x in space, or for all y in space, I should say. Pi y is approximately y in norm. But if pi has fewer than d rows, then it's going to have a non-trivial kernel. And that thing in the kernel is, anything in the kernel is not going to have its norm preserved, right? So you can't hope to have a linear embedding that gives you this guarantee. It's necessarily a nonlinear embedding. And there was previous work on this problem. So the immediate previous work was by these 4 authors, Mahabadi et al. They showed the exact same guarantee as our theorem, but with a worse target dimension. Instead of 1/n squared log n, they get 1/n to the 4th log n. And this is optimal. Our bound is optimal because even for the JL problem, where you just want to preserve distances within x, I showed with Caspar Green Larson that alone has a 1/n squared log n lower bound. Okay, and in fact, in this talk, both of the proofs of both the terminal upper bound as well as the JL lower bound, both of them are quite short. So my goal in this talk is actually to present both proofs. I'm going to show you both the proof of this terminal dimensionality reduction theorem, and I'm also going to show you the proof of the JL lower bound that shows that it's optimal. So I showed you computer science motivation for the JL lemma. What is the motivation for terminal dimensionality reduction, where you want to preserve distance to the rest of space? So the motivation, really, I think the strongest motivation is static data structures and adaptive queries to static data structures, which I'll talk about in a second. So what is a data structure? A data structure is just a way of laying out data in memory that allows for efficiently querying that data. And in a static means that the data doesn't change. So a static data structure keeps the database in memory and allows later queries. Non-static, the dynamic version would be you're allowed to update the database. I'm allowed to remove, let's say, a vector from the database or insert a new vector or change things in the database. Static means the database doesn't change. Okay, and what do you want from your static data structure typically for any data structural problem? You want to use little memory, and you want to support answering queries from a known family of queries quickly, okay? Meaning every time there's a query, you can answer that query quickly. Another thing you might also probably want is fast pre-processing time. Given the database, how long does it take you to create the data structure on that database? Okay. So for example, one family of queries you might want to support are nearest neighbor search queries, right? So you have a database of high dimensional vectors. Someone says query Q is a vector, and what you're supposed to return is the vector in the database that's as close as possible to, the closest vector in the database to the query, right? So for example, I have a database of fingerprint images, and then now, I collect a fingerprint from a crime scene, and I want to find the fingerprint in the database that's closest to the query fingerprint. Okay. Now, the problem with the JL is, you can say, well, let me speed up, let's say nearest neighbor search. Let me speed up this data structure by using JL, okay? The problem is you do know the database when you're creating the data structure. So you do know the database when you're picking the embedding F, but you don't know what the future queries will be, okay? So you don't really know what capital X will be, right? Capital X is the set of vectors you're supposed to preserve. But capital X basically includes all future queries that you're going to see, let's say, over the next day, but you don't know what that is. Now, there's a standard solution to this, which is to observe that in the usual proofs of the JL lemma, the Johnson-Lindenstrauss lemma, I said it's a linear map. X gets mapped to pi x. In fact, this choice of linear map doesn't even depend on the database. What you can do is just pick a matrix pi that has IID, Gaussian, or +/- entries normalized, and you can prove that with high probability, no matter what your database is, that matrix is good. That matrix works for your database. Okay. So it's oblivious to what the database is. So you can say, okay, good. Well, I didn't know what the queries were in the beginning, but that doesn't matter. I'll just argue about correctness on the current database as well as what all the future queries would be, right? So here I'm assuming that the user of this database who's coming up with the queries, is coming up with queries in a way that doesn't depend on the way that I'm choosing it doesn't depend on the randomness that I'm using to sample my matrix pi, right? I'm assuming that they're uncorrelated, they're independent. So the advantage though of terminal dimensionality reduction is that correctness is okay. So it satisfies the main one. Actually, I should have highlighted is the last bullet here, which is that you get a for all guarantee, which is once you know that your F satisfies terminal dimensionality reduction, then you'll work for all queries indefinitely. And the reason that's most important is adaptive queries. Okay, meaning suppose someone is doing some exploratory data analysis, right? And they query your data structure with some query Q, they get back an answer. And based on the answer they get back, they say, oh, that answer is interesting. Because you gave me that answer, I now want to ask this second query, right? So the reason they're asking the second query is correlated, right? The fact that they're asking the second query is correlated with the randomness. It's dependent upon the fact that you gave that answer to the first query. But the fact that you gave that answer to the first query is correlated with the randomness of your data structure, and the randomness being pi, right? So kind of implicitly now, future queries after the first query are correlated with the internal randomness of the data structure, which is a no-go, right? You're not allowed to ask queries that are correlated with the randomness of the data structure. Then the correctness guarantees are off. Okay. Does that make sense? That's an important point. So I want to make sure that, does anyone have a question? I'm happy to be interrupted right now with a question.
The only questions so far were to verify that the dimension D of the points you're embedding is independent from the number of rows you need in a JL.
It is, yes.
Yes.
That's right. The number of rows is not dependent on the dimension. That's right. Okay. Yeah, I mean, maybe an easy way to see this, right? Like the fact that you're not allowed to ask queries that are dependent upon the randomness of your process. I mean, for example, consider polling, right? So if the queries I'm going to ask about my sample polled people are fixed in advance, it's okay. Like I want to estimate the fraction of people that are going to vote for one candidate, political candidate over another. If I know that I'm going to ask that question, I can poll and ask that question and get error bars that make sense, right? But if I look at the polled people and then I base my question on the set of polled people, I can say, oh, okay, so now I look at the polled people, I see that Jelani Nelson was polled. And then now my query is going to be, how many people in America are named Jelani Nelson? Oh, look, 1 out of 100 in my sample is named Jelani Nelson. So I'm going to guess that 1% of America is named Jelani Nelson, right? That's bogus. Right? And the reason it's bogus is the fact that I'm asking that query is correlated with the randomness of the process, right? So that's exactly the same thing that's happening here. If you interact with this data structure repeatedly, if you ask many subsequent queries, then the fact that with the randomized JL, the fact that you're asking the second query is correlated with the fact that you had that particular matrix pi, right? And then the JL guarantees are off for future queries.
Is this similar to being able to, for example, ask a query that is in the null space of the matrix, for example?
Yeah, exactly, right? So if that happens, then definitely I'm going to be in trouble. Okay, so some history on terminal embeddings. So let's say I want distortion rho, meaning I'm willing to blow up or shrink distances by a factor of rho, and I want my target dimension after embedding to be m. So the first paper that gave any kind of result for this problem was by Elkin et al. They got rho to be arbitrarily close to the square root of 10, and their target dimension was log n. So if you want to be within additive epsilon of root 10, you have 1% squared log n. And their embedding is very simple. So what they say is, okay, my embedding, so first of all, just take a standard JL kind of embedding, an embedding that has low distortion for the original point set X. Now I want to extend it to the whole space, to all of RD. What do I do? So the first, if my original JL embedding maps to, R coordinates, my first R coordinates are going to be just apply the JL embedding, okay? And then now if my point set is a query point that's not in the original point set, then it doesn't necessarily make sense to say apply the original JL embedding because, this is a black box construction. It works even if your original embedding G from JL is not linear. So if your original embedding is not linear, then it's not clear how to apply that embedding to things that are outside of capital X because G is only defined on capital X as its domain. So what you do is you take the nearest neighbor to Q in the database, you apply G, the JL embedding, to the nearest neighbor. That's your first R coordinates. And then your last coordinate is just one more number, which is the distance to the nearest neighbor, the L2 distance to the nearest neighbor. Okay, so in particular, things in the original point set get mapped to the same as the JL embedding, comma, 0, one more coordinate that's 0, and everything else gets mapped to this thing. And the subsequent paper that managed to get distortion 1 plus epsilon by Mahabadi et al. Does something more complicated, okay? So it again finds the nearest neighbor. It applies the low distortion embedding on capital X to the nearest neighbor in the point set. It adds some offset Z. This offset Z is found by solving some semi-definite program, which we're going to talk about soon. And then there's something you put in the last coordinate. So again, both of these embeddings are just one more dimension, an additive one more dimension than a JL embedding. There's some bad news though, which is that there's some tightness, some sharpness to both of these previous works. So it seems like improving them, is improving them a lost cause. It's not because we did improve them, but let me describe to you what the sharpness was. So the Elkin et al. Paper, I told you what the embedding was, right? So the first few coordinates you just map to the embedding of the nearest neighbor, comma, the distance to the nearest neighbor. So if you just take these 3 points as your database, namely the 3 points on the real line, -1, 0, and 2 on the real line. And then now, you want to say that I preserve distance to all other points. I want to have an embedding that preserves all other distance to all other points in space. Let's say my new point in space is the point 1, also on the real line. So what does their embedding do? It maps the first coordinate. So let's even take now my JL embedding actually is just going to be an isometry. It's the identity map. Okay, the identity map has perfect distortion, right? It doesn't distort anything. So the nearest neighbor of 1 is 0. So the first coordinate is going to be 0 because it just applied the identity map to the nearest neighbor. And then comma, the distance to the nearest neighbor. The distance from 1 to 0 is 1. So 1 gets mapped to 0, comma 1. And then if you look at this picture, I increased my distance to 2 by a factor of √5. And I decreased my distance to -1 by a factor of √2. So overall, the ratio of stretch to contraction, the worst case is √10. So this this has distortion √10, which is basically sharp. Their analysis is sharp. Their analysis said you'll get arbitrarily close to √10 depending on the distortion of the original embedding. And the MMMR paper had a lower bound which said, look, if the strategy of your embedding is I'm going to find a good embedding. The strategy of my embedding is original points in the point set are going to get mapped to something, comma 0, or something, comma 1 more coordinate. And then every other point also gets mapped into something, comma 1 more coordinate. Okay. If that's your strategy, then and your strategy uses the fact that you have a low distortion embedding on the point set in a black box way, then you have to suffer a blow up in your distortion where if your original distortion was 1 plus epsilon, the new one is going to be 1 plus the square root of epsilon. Okay. So in particular, what maybe what I should say is, let's say that G is a low distortion embedding on the original point set capital X. Everything in the original point set, every little x in the original point set gets mapped to G of x comma 0. And then other points in space, you're allowed to embed them any way you want, okay? And then what they argue is that there are low distortion embeddings G for which they have distortion 1 plus epsilon on the original point set, but this extension of them to all of space will have terminal distortion 1 plus root epsilon. So there are G's where this doesn't work. So you cannot just use a low distortion embedding on capital X in a black box way and get better basically than 1 over epsilon to the 4th. Okay, because basically you need root epsilon to be epsilon, right? Which means your original epsilon really had to be epsilon squared. And we know there's a JL lower bound. So if you want to have a 1 plus epsilon squared distortion, you need 1 over epsilon to the 4th. Was there a question? Okay. So our main contribution, oh, Mark, were you about to say something?
There's just a question about going back and sort of showing the statement again, so one of the people watching can get the difference between n and d figured out. If you have a
n is, oh yeah, so okay, so there's a point set capital X. Capital X has size n. There are n vectors in your database. D is the original dimension of those vectors. Does that make sense?
Yep.
Okay. Great. So our main contribution is we don't actually change the MMMR embedding. We use the same strategy, okay? In fact, we solve the same semi-definite program they do. We take a low distortion embedding G on the original point set. We extend it the same way they do. The difference is they tried to use the fact that G was a low distortion embedding on the original point set in a black box way. And they ran into trouble. You know, they have a lower bound saying, you know, you can't do better than them if you're using it in a black box way. So what we do is we don't use it in a black box way. We condition on G satisfying more than simply being a low distortion embedding on capital X. Okay, so I'll tell you what is that more and how does the analysis look. So the more that we want G to satisfy is what I'll call convex Hall distortion. So let capital T be a set of vectors, and really vectors that are in the unit ball. So everything in capital T has norm at most 1. I'll say that pi, a matrix pi, has epsilon convex Hall distortion if this is true. If for all z in the convex hull of T, the norm of pi z and the norm of z differ by at most an additive epsilon. Now, how do we get good convex Hall distortion? Basically, there's a theorem that says, let's say that you have a set of vectors capital X, okay? And you want to preserve all distances within capital X up to 1 plus epsilon. That's basically the JL setup. You don't forget about terminal now. You just want to preserve capital X. So you can set capital T to be the set of all normalized difference vectors in capital X. So if you preserve all norms in T, multiplicatively, that implies that you preserve all distances in capital X. And what this previous work says is that the number of rows you need in, say, a random Gaussian matrix, i.e. Gaussian entries, okay, it could be, log n over epsilon squared works, that's JL. But in fact, there's something more refined than log n over epsilon squared that works. In fact, the more refined thing you can say is the number of rows you need is proportional to the square of the Gaussian mean width of T. And I wrote here what the Gaussian mean width of a set of vectors are. It's the expectation over a random Gaussian vector with identity covariance matrix of the maximum dot product of that Gaussian vector with elements in your set, capital T. Okay, so this thing is that, I'm not going to prove it for you. It's a simple argument. This thing by union bound is always at most root log n. So the square of it is at most log n. So G squared of T is always at most log n, but it could be better. Okay. And the insight here really is that the Gaussian mean width of a set of vectors as well as the Gaussian mean width of their convex hull is the same. Okay, so that's basically, the Gaussian mean width of a set of vectors of the convex hull of a set of vectors is also at most root log n. So that basically is enough to argue that if you take a random Gaussian a random pi that has Gaussian entries, not only does it have low distortion on a point set, but it also has low convex hull distortion by this theorem. Okay, so really where the MMR paper missed out was they tried to use the fact that pi has low distortion on the point set. Really, they should have been trying to use the fact that it has the stronger fact that it has lower convex hull distortion. And it's going to turn out that, and it still has that property with high probability. And it's going to turn out that that property is enough for us to push everything through and get our results. So let's keep going. Let me skip this. This is basically the main takeaway is that this theorem here lets you get convex hull distortion basically for free. And we're going to see that that's important. So we're going to now prove a lemma that says, let capital T be the set of all normalized difference vectors in your original point set. Then if pi, a matrix pi, provides epsilon convex hull distortion for T, then for every query point in space that might not be in the original point set, there is some z such that if you translate g of xq, remember xq is the nearest neighbor to q, g of xq plus z, if you translate it by z, and then you make your last coordinate the same thing that MMR was doing, then you don't just preserve distances to space by 1 plus root epsilon, which is what they got, you actually preserve distances by 1 plus epsilon. Okay, so you don't need to suffer this worsening from epsilon to root epsilon that they suffered. Okay, so as a corollary, you can get terminal distortion, 1 plus epsilon terminal distortion with m being 1 epsilon squared log n. Basically, the number of dimensions you need to get convex hull distortion. Okay, so the rest of the upper bound now, what I'm going to do is prove this lemma for you. And then once we're done proving the lemma, I'm going to switch to a lower bound for JL, which is also a lower bound for terminal JL. Question?
But I'm not sure I understand why the lemma implies the corollary. Could you explain again? Sorry, Jelani.
Oh, yes. So, so here's what we're going to do. Every original point in the point set is going to get mapped to g of x comma 0. So if you look at distances between those, let's say you have x and x prime that are both in the point set, you have g of x, the distance is just g of x minus g of x prime, the norm of that. But, you know, our pi satisfies JL, and it satisfies even more than JL. It satisfies this convex hull distortion. So we automatically will preserve distances within the point set. And this lemma says that you also preserve distances outside the point set. Because what we're going to do is, for every, we have to define our embedding f. So what is our embedding f going to do? F of q, where q is not in the point set, is going to be g of xq plus z, comma, the square root of this thing, okay? And the lemma, so the fact that we have the corollary is basically just the triviality from the lemma. The lemma says that this works. That's all the lemma is saying. The lemma is saying that...
You'll tell us what z is.
Yeah, I haven't told you what z is.
I see. Okay.
Z is going to come from solving some semi-definite program.
Ah, interesting. Okay. All right. Thanks.
Okay. So, which is the same thing that MMR was doing. Okay. So first, here's a lemma. It's not the same lemma as MMR, but it's very similar. It's not the same because they tried to prove a similar lemma without convex hull distortion, and they suffered a loss because of it. If this lemma seems to be the right lemma because you can get what you want without the loss. So here's the lemma. Consider a set of vectors Ti that are, and define the VIs to be their normalized versions, and define capital V to be, twice 2n vectors where you have the plus VIs and the minus VIs both. So capital V has size 2 times capital N. If pi provides convex hull distortion for capital V, then for all u in space, there exists a z such that, and for us, when we apply this lemma, u is going to be something related to q. I think u is going to be something like maybe q minus its nearest neighbor or something like that. We'll see in a second. There exists a z such that, first of all, z has bounded norm. Its norm is bounded by the norm of u. And second of all, you should think of z as being some approximation to u in the projected space. So U had some dot product with Ti. Z is going to have a similar dot product with pi times Ti. So Z is more like a substitute for pi U. So we're not actually mapping U to pi U. We're instead mapping U to Z. But Z, you should think of Z as like pi U, in that it's supposed to behave like U in the projected space. So all these dot products are preserved when you map from U to Z. So let me prove the theorem. This is what we want, right? We want that for all I, I'm just using the fact that VI is TI divided by its norm, okay? So for all I, Z times pi VI is close to U dot VI. Okay, so if I just subtract the right-hand side from both equations, from the inequality, I get that for all I, this difference is non-positive. Okay, and now I'm going to do a convex relaxation of this requirement. So here I have basically a set of 2 times capital N inequalities, right? Some constraints, some inequalities. And now what I'm going to do is I'm going to define capital lambda to be the set of all 2n. Now n is, when I say n from now on, it's capital N. So capital lambda is the set of all 2n dimensional vectors that have unit L1 norm. Okay. And capital B is going to be the unit ball, no, not the unit ball, but the ball in m-dimensional space with radius equal to the norm of U. Okay. And now what I'm going to say is, I'm going to define the following function phi, where phi takes as input U prime as well as lambda. U prime, you can think like Z is like U prime. And the thing that I want you to take away from this is, consider the case where lambda is the vector that has a 1 on the VIth coordinate and a 0 everywhere else. Just consider that for now, okay? So lambda V is 1 for VI, and it's 0 for all other coordinates. This lambda has unit L1 norm, right? What does this summation say for that choice of lambda? Everything in the summation dies except for the VIth term. And what you have is that U dot VI minus U prime dot pi VI minus epsilon times the L2 norm of U. And I'm going to want phi to be non-positive. Okay, so that's exactly the constraint from above. If I set lambda V, if I set lambda to have lambda VI being 1 and all other entries being 0, I get one of the constraints from above. And if I set lambda VI to be -1 and all the other entries to be 0, I basically get the other direction of, because this is an absolute value in the constraint. So I can basically get, the absolute value is basically saying that that thing is at most epsilon times the norm of U, and its negation is also at most epsilon times the norm of U. I can get both of those constraints by setting lambda to be either the basis vector for VI or minus the basis vector for VI. Okay, so basically I can get all those constraints via 2n choices, different choices of lambda. Okay, so now this is basically, if this is true, if it's true that there exists a Z such that for all lambda, there exists a Z in the ball B. So there exists a Z in capital B such that for all lambda and capital lambda, phi of Z lambda is non-positive. That's an even stronger statement than saying that all my inequalities are satisfied, right? Because I'm satisfying it for the standard basis vectors and also other vectors in the L1 ball that I don't even care about. Okay. Does that make sense? So I basically strengthened, I've strengthened my requirements by forcing it to be true not just for these lambda, but for all lambda in the L1 ball. Okay. So why did I do that? It seems like I made my life harder. But the reason I did that is because now I can apply a minimax theorem. A minimax theorem says, look, if I'm optimizing over a convex function in a convex domain, I basically can swap the order of the min and the max. So to say that there exists a Z such that for all lambda this thing is non-positive, it means that the min over all Z, the min over all Z of the max over lambda is non-positive. but the min of the max is equal to the max of the min by minimax. Okay, and I was able to apply minimax by moving from these 2n choices of lambda to all lambda in the L1 ball because I've convexified my region. So now I just need to show that the max over lambda of the min over u prime is non-positive. So I just need to show that the right-hand side is non-positive. So I need to show that for a fixed lambda, there's a way to make the phi non-positive. I can minimize the phi and make it non-positive. And the way I'm going to minimize the phi is I'm going to define a point to be the sum over v of lambda v times v. And then now take this vector here that I've defined, which is pi p over its norm times the L2 norm of u. And I think I'm running a little low on time because I do want to say something about the lower bound. But kind of once you apply minimax and define the minimizer u prime in this way, it's and I'll just show it here. It's just follows immediately from convex Hull distortion. And I don't want to dwell on this because it's I'm just going to use up my time, and I think it's not super interesting. But the punchline is that convex Hull distortion of pi basically implies that this thing is non-positive. Okay, so you get your lemma from convex Hull distortion. Okay. By minimax, you've shown what you want. You've shown that there exists a z in this ball B that satisfies all these constraints, namely 1 and 2 above. So now how can I use this lemma to prove the final theorem? Okay. So we're going to take the TIs to be xi minus xq, where xq is the nearest neighbor to q in the database, and u is going to be q minus xq. Okay. And now I want to argue that the distance between f of q and f of x is preserved, where x is some xi in the original database. So you look at f of q minus f of xi, look at its L2 norm squared, and expand that, right? Just use the fact that a minus b L2 norm squared is a squared plus b squared minus twice the dot product. I don't know, is that called parallelogram rule? Okay. And do the same expansion for q minus xi. You'll notice that these two things look quite similar, except the first terms cancel out, and then I have these other terms that don't quite cancel out, but one has pi's, one doesn't have pi's. One has q minus xk, one has z. Okay, and then I want to argue that these things are small. These differences are small. Okay, and again, let me not dwell on a sequence of inequalities in a Zoom talk, but they are small. Okay, so it follows basically immediately from the lemma and some simple manipulations that these things are small as you wanted them to be. Okay. And I think this is being recorded on, it's going to show up on YouTube later. So, you can go to, if you want, you can look at this on YouTube and, or look at the original paper and see, just verify these inequalities yourself. I gave the reasons written right on there. Okay, so that's basically it, okay, for correctness. What's the algorithm to compute f of q? The analysis says we can set, sorry, this is not quite correct. So f of q is this, right? It's pi, it's pi, if q is not in the point set, it's pi times xq plus z, comma, the square root stuff, blah, right? So to compute this, I just basically need to compute xq, that, I can do that in polynomial time. I just scan and find the nearest neighbor. And then I need to compute the z. The z comes from the lemma. So sorry, this is a typo. F of q is not z. F of q is what's on the last slide, but the main thing that I need to compute, the most expensive thing to compute to get the embedding is I need to figure out what z is. Okay, so what do I need z to satisfy based on the lemma? I need z to have a bound on its norm. And I also need that for all I, z, the dot product of z with this vector is close with this other dot product. Okay. So for fixed I can express the second set of inequalities by some linear constraints. Z dot alpha is at most something, and z dot alpha is at least something. I need 2 because I have an absolute value there, so I need to have it in both directions. Okay, so I have basically 2n linear constraints, as well as a ball constraint, a norm constraint. And that can be captured with semi-definite programming. So you can solve this with an SDP solver in polynomial time. If you don't, it's definitely, you can hopefully clearly see that it's definitely a convex program, right? I'm trying to find Z in the intersection of a Euclidean ball and a polytope, okay, the separation oracle is just, well, either I don't satisfy the ball constraint, and then I have my separation oracle, or I don't satisfy one of the linear constraints, and that linear constraint itself is a separation oracle. Okay, but so you can use ellipsoid. You can clearly use ellipsoid here, but you can also cast this as an SDP.
Oh, John, I have another question.
Yeah.
Just to make sure I understand this correctly. So do you have to solve a semi-definite program for each point, or just one semi-definite program in the beginning, and every time you get a point is always...
No, every time you get a query Q, you need to solve an SDP to figure out where Q gets mapped.
I see. So you need a nearest neighbor search and an SDP for each Q?
Yes, which is not good, and I'll talk about that as an open. That's an open problem, is to how to speed that up.
Quick stupid question, if I can. Does anything break in the proof if I use a faster approximate nearest neighbor point instead of the true nearest neighbor? I would assume not, but.
You'd have to be, so the place where that really shows up is the very last inequality here. You see where I say triangle inequality? Mm-hmm. Somewhere there, I'm using the fact that I can replace a Q minus XQ with Q minus XI, and it'll only go up because XQ is the nearest neighbor. But if I'm using something that's an approximate nearest neighbor, I mean, if I understand just how approximate it is, like if it's a multiplicative, on this distance, then I probably can still get something.
Okay, thanks.
Okay. Any other questions? Okay. So optimality. So again, this is the theorem, the terminal dimensionality reduction theorem, and the claim is that this 1/n squared log n is the best possible. In fact, it's the best possible even for the original JL problem. Okay, so the original JL problem says even if I'm trying to preserve distances within capital X. So some history on this. The original JL paper itself even said that for the JL problem, there's a lower bound of log n. This lower bound was not sensitive to epsilon. So if you send epsilon to 0, their argument would basically just improve the constant within the big omega, but it wouldn't it wouldn't grow to infinity as epsilon goes to 0. Then there's another paper by Noga alone, which showed 1/n squared log n is a lower bound, but there's a loss here of log 1 over epsilon. And then I had a paper with Casper, Green, Larson that showed if you want your map to be linear, then you can't beat JL. But it's still left open the possibility that you could beat JL with a nonlinear embedding. And that's the thing that the most recent work shows, is that there are point sets where good embeddings that beat JL just don't exist. It doesn't matter whether they're linear or not, they just don't exist. And I'm going to show you the proof of that because it's a very short proof. So here's the theorem. For any dimension d, for any number of vectors n, and for any epsilon that's not too small, there is a set of endpoints in Rd such that any embedding to any map into dimension m must, with distortion at most 1 plus epsilon, must have target dimension at least 1/n squared log n. Okay. Now, you might wonder why do I have this range requirement on epsilon? That epsilon is not too small. Notice that I can always embed in dimension d with no distortion, but via the identity map, and I can also always embed into dimension n with no distortion either, because my n vectors span at at most an n-dimensional subspace of Euclidean space, so I can embed them in dimension n with no distortion at all. In fact, I can translate them so that one of them is the 0 vector, and now they span an n-1 dimensional subspace. So I can even embed in dimension n-1 with no distortion. So you're never going to be able to prove a lower bound better than n or d. You're never going to be able to prove a lower bound better than the min of n and d. So if the JL bound 1/n squared log n, if that bound is bigger than the min of n and d, then it's not a lower bound, right? It's not a valid lower bound. So our condition in the theorem is basically just saying that as long as you're not right up on these two trivial embeddings, the identity map and this other one, then the lower bound holds. So as long as the JL bound is sufficiently far away from the min of n and d, then the lower bound holds. So our proof is via an encoding argument, which is just another name for the pigeonhole principle. So we do not give an explicit hard point set for JL. We just show that there is a point set that where you can't beat JL. To this day, I still don't know what that point set is. How do we do it? We define a large collection of point sets. Each one of these point sets has endpoints in RD, such that if each point set in this collection can be embedded much better than the JL bound, then I say surjection, that's a typo, it should say injection. There's an injection from this collection of point sets. So each point set is going to get mapped into a bit string of length t, such that this injection is mapping this collection into a smaller set, which is a contradiction. You can't have an injection from a bigger set into a smaller set, right? So if I'm mapping into a t-bit string, t had better be at least logarithm of the size of the collection, but I'm going to show you that I can beat logarithm of the size of the collection, which is a contradiction. So it must not be the case that every point set in that collection can be embedded better than JL, right? There must be one that cannot be embedded better than JL. That's the only assumption I made here. Okay, so how does the encoding argument work? The first observation is that preserving distances implies preserving dot products, right? So let's say that x and y have unit norm. You can show that if you preserve the norm of x and you preserve the norm of y and you preserve their distance, then the dot product of f of x and f of y is close to the dot product of x of y. Okay, you can show that. This follows again from the parallelogram rule. And this is those two things that I highlighted in blue. They will be true if the distance to 0 is preserved, and I can just make every point set in my hard collection contain the point 0. That way, those two things do hold. So okay, so now what does a point set in my collection look like? And in fact, it's not going to. I lied a little. It's not going to be a point set. It's going to be each point set in the collection is actually going to be an ordered sequence of points, possibly with repetition. So for a subset of coordinates, so S is a subset of coordinates of size k, I'm going to define the following vector ys, which is just the indicator vector of S. So it has a 1 for each thing that's in S and a 0 for each coordinate that's not in S. And I'm going to normalize it by root k so that it has a unit norm, unit Euclidean norm. And the key thing here is that if I take the dot product of this vector with the I standard basis vector, that dot product conveys information. It tells me whether or not I is in the set S or not in the set. If it's in the set, the dot product is 1 over root k, which is 10 epsilon by choice of k. If it's not in the set, then that dot product is 0. Okay, and the point here is, look, if my encoding, this is not exactly what we're going to do, but we're getting there. If my encoding doesn't keep the actual point set, but keeps the embedded version, which hopefully I can encode more cheaply because it's lower dimensional, then that embedded version still conveys this information of whether I is in S or not, because dot products are preserved by low distortion embeddings, right? So originally the dot product was either 10 epsilon or 0. Now it's either between 9 and 11 epsilon, or it's between minus epsilon and epsilon. But those are still two disjoint intervals. So I can still ascertain which case I'm in and still know whether I is in S or not. So if I just query my encoding for all these different dot products, I can know which of the D coordinates are in S and which are not in S. And basically I've just recovered S, which means I've decoded, right? And the fact that I'm able to decode, well, I don't know what's going on. The fact that I'm able, somehow my keyboard is going nuts. Let me see if I can. Sorry, I don't know what's going on. Is this still being shared?
Yes. Yep.
Okay, so I'll see the slides like in full screen.
Okay, so it's back in full screen, right? Okay, great.
Yeah.
My mouse went nuts. Okay, so the point is, by keeping encodings of the embedded vectors, that conveys enough information for me to know, for me to decode S. And the fact that I'm able to decode means that the encoding was an injection, right? You can't uniquely decode unless your encoding was an injection. So capital script X is going to be the collection of all ordered sequences of points that look as follows. It contains 0, E1 up to ED, together with a bunch of YS's chosen, with replacement possibly from the set of all subsets of 1 to D of size K. Okay. So the collection script X has size D choose K to the power n minus D minus 1, because each one of those YS's could be anything. Okay. From that set of size, from that collection of size D choose K, which is the set of all K size subsets. Therefore, any encoding requires the logarithm of that number of bits, which is nk log D over K. And right now, I'm going to assume that D is equal to n over log 1 over epsilon. There's no valid, there's no reason, there's no justification for me to make that assumption. D and n are different parameters. D, you can't assume that D is a function of n. D could be something, n could be something else. But let me make that assumption now, and then it turns out that that assumption can be removed at the end. Okay. So if I set D to be n over log 1 over epsilon, then this lower bound is saying that nm, my encoding length is nm. Remember, what I told you was, I'm going to be able to show that if I can embed anything in script X into m-dimensional space, that implies that I can encode into nm bits. Okay? Therefore, nm has to be at least the logarithm of the size of script X, so nm has to be at least nk log D over K, cancel the n's, m has to be at least k log D over K, which is exactly what I wanted, if epsilon is not too small. Okay? So now I just need to show this part. Why is it true that a low distortion, the fact that I have a low distortion embedding into m-dimensional space for every one of these point sets, why does that imply that I have a low bit length encoding? Why is that true? Okay, so why can't I have a question for you. Why can't I just make this my encoding? So okay, so I have a low dimensional embedding f for my point set. My encoding will just be, I'll write down f of 0, I'll write down f of E1, etc. in order. I'll just write them down for each vector in my point set. That's my encoding. So it used to be ND numbers, now it's NM numbers. So here's my encoding of length NM. So audience, do you see why this doesn't work? Any takers? No? So the problem is, remember what I said, I am encoding into bit strings of length t, right? This is not a bit string. This is a sequence of nm real numbers, okay? So I don't get any violation of, remember I'm trying to get an injection from a finite point set into a smaller finite point set. Now I have a map, my encoding is from a finite collection, script X, into a sequence of real numbers. That's not a finite encoding. That's not a finite length encoding. So this is not a finite length encoding. It doesn't violate pigeonhole principle. It doesn't violate what I want to violate, namely that I'm embedding into a smaller set. So here's a natural thing to try. Why don't I just round these numbers to finite precision? So each entry of these vectors is a real number. I'll just round it to finite precision. And in fact, that sort of works. So you can show that if you round the entries to integer multiples of gamma, where gamma is this, epsilon over root m, a Cauchy-Schwarz shows you that that's enough. Because what do I lose by rounding? Remember, I still want to be able to know the dot products up to an additive epsilon. If I know the dot products up to an additive epsilon, I can decode. So I need to make sure that my rounding doesn't change the dot products too much. And you can show that. If I round to these integer multiples of gamma, where gamma is this, the dot products don't change by that much, by more than an additive epsilon. Therefore, I can still decode. Now I get my contradiction. Now I have an encoding of length nm log 1 over gamma. And therefore, nm log 1 over gamma has to be at least the logarithm of the size of script X. That gets you a lower bound that looks like this. If you solve for m, because here you have m on both sides. If you solve for m, it basically gives you no-go-Lown's lower bound, but with an extra log n on the right-hand side. A slightly better fix I don't want to get into is, what is this doing? It's basically rounding in an L infinity net. And what you should observe is, if I'm trying to preserve dot products, it doesn't really make sense to round in an L infinity net. I should round in an L2 net. And if I round in an L2 net, I can basically get no-go-Lown's lower bound, and I get a shorter encoding. So I can get, let me just zoom here. I basically can get exactly no-go-Lown's lower bound if I round to an L2 net. Instead of, so I get 1 squared log n over log 1 over epsilon. But it's a very different proof from no-go-Lown. That's not what I promised you though, because this still has the extra log 1 over epsilon. So let me now, in my last couple minutes, remove that, show you how to remove that. So in order to decode, we just needed to know all the dot products between standard basis vectors and YS's. In fact, it's enough to know those dot products between the embedded versions. And in fact, it's enough to know those dot products between the L2 net roundings of those embedded versions. So the tilde is the rounding in an L2 net. So what's the thing we actually need to know? Let me write it in this matrix notation. So capital A is this matrix, which has as rows the embeddings of the standard basis vectors rounded inside of an L2 net. If I know A times this vector, which is the rounding in an L2 net of the embedding of YS, that A times that vector is basically all the dot products. So if I know all the VJs, I can decode. That's what we've been saying. But in fact, notice I don't even really need to know all the VJs exactly. I just need to know the VJs rounded in an L infinity net. Because each one of these dot products on the right-hand side is either going to be very close to 0 or very close to 10 epsilon. So if I know it to within another additive epsilon, it's still either really close to 0 or really close to 10 epsilon. Okay, so how can I leverage this to do better in my encoding length? Let E be the following linear subspace. It's the column space of A, which is at most m-dimensional subspace of RD. And define capital K to be the following convex body. It's the intersection of that linear subspace with all vectors in RD that have L infinity norm at most 13 epsilon. So it's the intersection of an L infinity ball with a subspace. Now, the observation is, look, all these things here, all these vectors Vj, they live in that convex body, right? Because originally all the dot products were either 0 or 10 epsilon. Now they're either close to 0 or they're close to 10 epsilon. So in other words, they're at least minus 3 epsilon and they're at most 13 epsilon. So they all live inside of a 13 epsilon radius ball in L infinity, and they also all live in this subspace because they're all in the column space of A. They're A times something. And now the thing is, this is just a fact about covering convex bodies or nets of convex bodies. K has a 1/13th net in its own norm, right? Convex bodies define norms, namely everything in the body is the unit ball of that norm. So symmetric convex bodies. So K has a 1/13th net in its own norm of size at most exponential in its dimension. This is a standard fact in convex geometry. So what I'll do is I'll define Vj tilde as the closest point in this net to Vj. And it just takes me logarithm the size of the net to specify Vj tilde, which is only m bits, O of m bits. So I'm done, right? And I'm almost done. I'm almost out of time here. The reason I'm not quite done is that if you look at this from the decoder's perspective, what does the decoder get? The decoder gets basically the names of a bunch of net points in this convex body K in its own norm. The problem, though, is from the perspective of the decoder doesn't know what K is because K depends on A, right? K depends on E. E is in the definition of K. E depends on A. A depends on F, right? Each point set in script X has its own F, right? So since the decoder doesn't know what the point set was, it doesn't know what F was, right? So it doesn't know, it doesn't know what the net is, so it doesn't know how to decode. So the way we're going to fix this is we're going to just, as part of the encoding, we're going to write down A explicitly. And it turns out that we can do that in bounded precision as well. And overall, we get an encoding of length nm as I promised you, and it works. So, you know, that's basically it. There is something you have to do to handle the case when d is not exactly equal to n over log 1 over epsilon. I'll leave this here. You can go check the YouTube. It's a very simple trick that was pointed out to us even by Oded Regev. Before that, we were doing something a little more complicated, but there's a very simple argument that gets out around it. Some open problems that I'll leave you with, and then I'm done. Give a way to do terminal embeddings quickly. So someone asked a question about this. Right now, in order to do a terminal embedding, in order to imply the terminal embedding to a vector Q, you need to first solve nearest neighbor and then solve a semi-definite program. Now, if the motivation of terminal embedding is to speed up nearest neighbor search, then it's pretty useless that to do the terminal embedding, step 1 is to compute the nearest neighbor, right? That's circular. You're not going to get speed up for nearest neighbor if step 1 is to compute the nearest neighbor. So can we get a sublinear time algorithm? And you know, solving the SDP is even worse. That's some polynomial time algorithm, which is even superlinear in it. So can you do this? Can you actually get a terminal embedding that can be applied in sublinear time? There's some other questions that I'll leave open here. Also understanding what is the behavior of the JL lower bound as epsilon and the upper bound as epsilon approaches 1 over root n or 1 over root d. So that's what I'll leave you with, and then that's it. And I'm happy to answer questions. Sorry for running a few minutes over time.
Oh, no problem. Thanks a lot for coming to talk to us. So we have, we'll wait a second for people to ask any last questions here at the end, and the other organizers and I can sort of